Okay, it's done.
Okay, so good afternoon, everyone. Today we are going to have a talk from Dr. Keaton Bell. Keaton completed his PhD thesis from the University of Texas at Austin in 2017 in white dwarf asteroseismology. After 2 years of working on solar-like oscillations at the Max Planck Institute for Solar System Research, he's now on NSF Astronomy and Astrophysics postdoctoral fellow at the University of Washington and a member of the Dirac Institute. So Keaton, thank you very much for accepting our invitation, and you may start when you are ready.
All right, yeah, thank you. Hi, thanks for having me. I'm really glad I could join you in this remote way during this crazy time. I hope that the people in your department and in your lives are doing well right now. So today I want to share with you some of my newest ideas and projects that my students, colleagues and I have been working on related to the analysis of TESS data, especially in pursuit of more accurate white dwarf parameters in combination with Gaia astrometric data. But let's start with a quick review of white dwarfs and why you might care to understand them better. White dwarf stars are compact objects packing about 0.6 solar masses into the space of the Earth. They are supported against further collapse by electron degeneracy pressure, and as a result, more massive white dwarfs are smaller than less massive ones. Their high gravities cause them to stratify chemically, with the heaviest elements diffusing towards the center and the lightest elements floating to the surface. About 85% of white dwarfs have hydrogen-dominated atmospheres, with most of the remaining white dwarfs having helium-dominated atmospheres. After they form dense and hot, white dwarfs evolve further by cooling, which is a fairly simple process, though made a bit more interesting by things like core crystallization or cooling through neutrino or possibly axion particles. This evolution by cooling allows us to connect white dwarf temperatures or luminosities to cooling age. So white dwarf stars are often used as chronometers for stellar populations, and have even been used to determine an independent age of the Milky Way. White dwarfs are the progenitors of type 1a supernovae that explode when mass transfer in a binary causes them to exceed the Chandrasekhar mass of 1.4 solar masses. And because type 1a supernovae serve as an extragalactic rung of the cosmic distance ladder, our understanding of how white dwarfs explode is important for studies of the accelerating expansion of the universe from dark energy. The vast majority of stars in the Milky Way, everything less than about 8 solar masses on the main sequence, will conclude their evolution as white dwarfs. And so white dwarfs serve as an observational boundary condition for constraining the whole of galactic stellar evolution. And I'm especially interested, although I won't get into it today, in the population of planets that orbit white dwarfs, as they tell us which planets survive the tumultuous late stages of stellar evolution. The interiors of white dwarfs harbor extreme physical conditions, providing remote cosmic laboratories for studying the equation of state under temperatures and pressures that are not attainable in terrestrial laboratories, and which are relevant to fusion energy production on Earth. And finally, some white dwarfs pulsate and can be studied with the tools of asteroseismology, which will be the main topic of this talk. And all this is dependent on how accurately we understand white dwarf stars. And so I seek a more accurate understanding of these interesting objects. So to study white dwarfs, we need to identify them. Here is the distribution of known white dwarfs on the sky circa 2018. The go-to method for characterizing white dwarf stars for the last 25 years has been the so-called spectroscopic method, where spectra are obtained for a white dwarf, like you see here, This spectrum shows Balmer line absorption of a hydrogen atmosphere white dwarf. And the absorption line profiles are then fit to models, as shown here in red, to provide the atmospheric parameters of effective temperature and surface gravity, or usually log surface gravity. And so white dwarfs are often presented in the context of this spectroscopic parameter space, this is oriented similarly to an HR diagram with more luminous stars typically towards the top, larger stars towards the top, and redder stars to the right. It's a happy accident that the colors of white dwarf stars are quite similar to quasars, which the Sloan Digital Sky Survey was keen to study spectroscopically. So SDSS has obtained spectra of tens of thousands of white dwarfs, which your own Kepler and collaborators have applied the spectroscopic technique to, characterizing one of the most important samples of white dwarfs for further research. You can see the SDSS survey footprint dominating the map of known white dwarfs here. However, there are some concerns about the accuracy of parameters derived from the spectroscopic method, as the line profile physics may be incomplete, and the method is prone to systematic observational errors as well. So recent parallax measurements from Gaia provide another way to identify white dwarfs. Stars can appear faint either because they are far away or because they're intrinsically faint. White dwarf stars are faint because they're so small. So they have much larger parallax motions than other types of star with the same colors and apparent magnitudes. And you can see here that the white dwarfs are clearly separated out from the main sequence in this Gaia HR diagram. So from Gaia DR2, Nicola Gentile-Fusillo et al. Cataloged 260,000 high likelihood white dwarfs all over the sky. And you can see these in this updated map of white dwarfs. So not only has Gaia provided a much more complete sample of bright white dwarfs in the recent years, but the astrometric measurements provide an alternative avenue to the spectroscopic method for constraining white dwarf parameters. As white dwarfs cool, such as along the evolutionary path traced out in this diagram, they pass through different instability domains where they may pulsate depending on their compositions. Very hot white dwarfs, some still the central stars of planetary nebulae, pulsate at very high temperatures. But I work mostly on these cooler pulsating white dwarfs with their instability domains circled here, the DBV and DAV pulsating white dwarfs. These are helium-atmosphere and hydrogen-atmosphere pulsating white dwarfs, respectively. And they pulsate when they cool to specific temperature ranges where the ions in their plasma atmospheres begin to recombine with electrons, creating a partial ionization zone where photons get dammed up and the white dwarfs develop an outer convection zone that enables and releases energy in such a way to drive global oscillations. These oscillations are standing waves that propagate through and are affected by the interior of the white dwarf. And they cause the star to vary in brightness at multiple simultaneous frequencies. These are the eigenfrequencies of the star as a physical system. And comparing the measured eigenfrequencies to frequencies calculated for stellar structure models is the primary method of probing the interior conditions of white dwarf stars, a process known as asteroseismology. So on the right here, you see an animation of what the variable surface of a white dwarf might look like to produce the overall record of brightness variations that are displayed in the bottom of the figure here. Such records of brightness variations are obtained from time series photometry, where a pulsating white dwarf is repeatedly imaged, and then the apparent target brightness is measured from each image. I like to think of this as a video study of the stars. And so now I want to introduce an outstanding new video camera. This is TESS, the Transiting Exoplanet Survey Satellite, which is currently providing some of the best data on variable white dwarf stars. Similar to the Kepler spacecraft, the primary goal of TESS is to detect and characterize transiting planets. These are planets that pass in front of their host stars, and that we can measure the slight dimming of their stars from. But these same precision photometric records that are useful for the transit method, these photometric records of star brightness are exactly what we need to do asteroseismology. And both Kepler and TESS have been a bonanza for variable star science. TESS just recently completed an initial 2-year survey that obtained full frame images every 30 minutes for between 27 days, all the way up to a year, as shown in this map. And that covers about 85% of the sky. And then for select stars of interest, images were saved every 2 minutes. Because typical white dwarf pulsation periods are around 10 minutes long, the TESS Asteroseismic Science Consortium Working Group on White Dwarf Stars and Subdwarfs has ensured that every bright white dwarf is observed with the 2-minute cadence. TESS is now operating in an extended mission, saving full frame images every 10 minutes and providing a new 20-second cadence. And I have to show this TESS mosaic video that was just released earlier this week. It shows the final survey footprint in TESS images, and you can see the Milky Way standing out spectacularly. There's precision photometry available for tens of millions of stars in this data set. And while I'm focusing on the white dwarfs, a lot of the tools I'll be discussing are applicable to any analysis of TESS data. And I'll start with the tool Pyriod. Pyriod. This is a frequency analysis software for Python that I've been working on. My goal has been to provide the functionality of a widely used Java program, Pyriod 04, to the modern astronomy workflow in Python. This is an interactive package that plays nice with the popular light curve package for manipulating space-based photometry data. Here I show the light curve and the Lomb-Scargill periodogram from TESS observations of a pulsating helium-atmosphere white dwarf, which was the subject of a first light paper from the TESS Asteroseismic Science Consortium. Well, the variations in brightness are not immediately obvious from the light curve, the pulsation signals are very clear in the periodogram where they stand out above this noise floor. And we can directly read off the amplitude and frequency from this plot. But Pyriod is not just made for displaying these data, it provides tools to fit them with the pre-whitening algorithm. This is an iterative procedure, the first step of which is to identify the most significant signal in the data. Here, this is highlighted with a black dot. And with the click of a button, the signal is added to our frequency solution. And the best fit of a sinusoid with that amplitude and frequency to the light curve is obtained, as shown here. So this looks like a big red band across the light curve, but that's actually our current model with such a high frequency sinusoid in it that it's basically just scribbled over itself, but I'll show that in more detail in a second. The periodogram updates to display the periodogram of the residuals in blue. That's the difference between our current time series model and the light curve, as well as the periodogram of the current model. So this basically lets us quickly see which signals are already in our model and what still needs to be fit. So the steps of selecting the most significant signal are just repeated for this next point, and then we can do it one more time. And each time we're refining a multi-sinusoid fit to the light curve. But with these next signals, we have to be careful because they don't actually represent independent modes of pulsation. So the nonlinear response of the star to pulsations causes pulsational variations to not be strictly sinusoidal And this difference in their pulse shape causes signals to show up in the periodogram at sums, multiples, or differences of independent pulsation frequencies. And these next three signals are related to the ones we've already measured in this simple way. So since in asteroseismology, we want to compare measured pulsation frequencies to model pulsation frequencies, we need to identify all of these so-called combination frequencies and exclude them from these comparisons. These are not independent eigenfrequencies of the star. So Pyriod allows us to fit combination frequencies, enforcing their arithmetic relationships to the fundamental pulsation frequencies, which can improve our constraints on the individual pulsation frequencies involved. While I won't go into any further detail in this talk, the relative amplitudes and phases of combination frequencies can actually be used to help identify the standing wave patterns of pulsations at the star's surface, which is really important for correctly connecting the measurements to asteroseismic models. And I'm collaborating with Mike Montgomery and an undergrad at the University of Texas at Austin in an effort to use Pyriod to do just that. So we fit these combination frequencies, we continue the pre-whitening process until all statistically significant signals in the periodogram are included in our model, and we get this final solution. So I'll zoom in on the time series a little bit to show in more detail. This is 1 day of data. You can't really see these signals, from the data themselves, but you see that from our model, what we suspect is happening in the star intrinsically, and that we're able to resolve these signals because of the length of the TESS data set. But imagine if we had just one night of time on a ground-based telescope, we might only hope to observe, say, a third of this time span, and this is usually not enough to provide this wouldn't provide a significant signal or frequency resolution to detect such signals like this. And even multiple nights of ground-based data can usually not provide an accurate frequency solution because of aliases introduced from daytime gaps in the data. But here, this is not a problem. We end up with a table of 9 independent pulsation signals and 10 combination frequencies. The frequencies listed here are in units of microhertz. Typical values are in thousands of microhertz, and the uncertainties from 27 days of test data are in the order of hundredths of microhertz. So quite precise frequency determinations. The table view of the frequency solution in Pyriod is interactive. You can modify these values manually. You can also, there's checkboxes available. You can hold any of the frequencies, amplitudes, or phases affixed to specific values so that they won't vary when you refine the fit, which can be helpful for imposing any additional external constraints that you have. And so that's I just want to give that demo of the software I've been working on, but and show how we make this full analysis of the TESS light curve of this pulsating white dwarf. But before we go and make the comparison of these signals to asteroseismic models, we need to check one thing. We've got to make sure that the signals detected come from the star that we're interested in. And that may sound trivial, but while TESS provides excellent frequency resolution, its spatial resolution is really quite poor. TESS has a plate scale of 21 arcseconds per pixel, meaning each pixel contains a large amount of sky. In this figure, you can see in blue the outlines of each pixel overlaid on an image of the same field from the digitized sky survey. This is the field for that pulsating white dwarf we just looked at. You see it, that single pixels can contain multiple stars, and considering that each star spreads its light across the detector, across many pixels, it's rare for any TESS TESS pixel to only contain significant light from a single star. You can get a sense of how much the light spreads out from the red outlined aperture that's used to extract the photometry here. Almost all TESS light curves are blends of multiple sources. So this part of my talk is highlighting work that Michael Higgins, a new graduate student at Duke University, is leading, which he began as an undergrad at UW last year. This is another view of the same thing, but this is the field in the actual TESS data. You can see how large these stars appear on the detector. The gray dots indicate the location of Gaia sources. If you can see, some of these are quite faint. Michael's developing a software that enables us, what it does is it takes that set of frequencies that we fit with Pyriod, and it determines where on the sky those signals are centered. What we're asking is, where on the sky are these signals we detected coming from? We want to check that they're coming from a position consistent with the star we're interested in, or inconsistent with the star we're interested in. And we do this by simultaneously fitting the spatial and temporal data with these signals. This image shows that for our pulsating white dwarf star, those signals are only present from a specific part of this image that we fit the location of with an X, and that agrees very well with the location of the white dwarf from Gaia, which is the red dot in this image. So okay, the result of this analysis is that the signals that we measured in the TESS light curve of this white dwarf do appear to come from the location of the white dwarf on the sky. So that's a good thing. But it's important to confirm this as part of every analysis of a variable star with TESS. And to make this point, let's quickly look at another pulsating white dwarf. This hot DOV pulsator is from a set of stars analyzed in a recently submitted paper by Alejandro Corsico. And it caught my eye because it showed both the typical signatures of pulsations, these signals marked in blue, as well as a series of low frequency harmonics, which are typically indicative of binary eclipses or planetary transits, which would have been super exciting to have, in combination with pulsations from a hot pulsating white dwarf star. But knowing how big the TESS pixels are on the sky, I knew there was some risk that these two types of signals come from two different blended sources. And in fact, perhaps it's very likely, as this is a much more crowded field with dozens and dozens of stars contributing light to the light curve extracted from the pixels in red. So I asked Michael to weigh in on this. So we separated out the pulsation signals from the eclipse signals according to how we've color coded them here. And Michael fit the locations of central power for both sets of signals separately. He found that the pulsation signal was at the center of the image where our target star was located, but the signals from eclipses were significantly offset to a different part of the TESS postage stamp here. And just to confirm this result that these eclipses do not belong to the white dwarf system, I extracted the light curves from the hottest pixel in each of these images, those ones with the red circle around them. And you see that this produces a much clearer signal from the eclipses, confirming that they really do come from this other part of the detector, and they just bled into the aperture that we were using. And so I emphasize this process because I think that misattributing variability to the wrong source is going to be one of the most common problems in the literature surrounding TESS data. And all TESS analyses should really include tests like this. So Michael and I are wrapping this project up and plan to release a public software tool for this type of analysis in the coming months. Well, back to our helium-atmosphere white dwarf. We now have this this great frequency solution. And one of the valuable bits of asteroseismic information that we can determine from this is the mean period spacing of detected pulsation modes, which represents a radial overtone sequence of standing waves. We performed 3 similar tests on the period list to reveal a preferred spacing of around 38 seconds for this star, which is typical for a non-radial standing wave pulsation with one nodal line on the surface. When we use this as a starting point for fitting a mean period spacing with a line, we get this result. You can see the best fit here. It's a little smeared out. We included some uncertainty about what rotational components of the pulsations we're observing to include that. The residuals, the difference between this fit and the points, can actually contain some interesting information from mode trapping. This pattern of residuals here is potentially could help us constrain the location of different features in the depths of the star. And then I show the predicted location of modes with this mean period spacing in the periodogram here shown in period space as these vertical dotted lines. And you can see where how the points we've detected, the signals, the independent signals that we detected, line up with those predicted locations very well. And so, so one of the cool things about doing this project as a consortium effort of the TESS Asteroseismic Science Consortium is that we had asteroseismic analyses contributed from 2 different groups. There was the Argentinian group from La Plata using fully evolutionary models that was led by Alejandro Corsico, and then the so-called Texas group led by Agnes Bischoff-Kim from Penn State Scranton using a grid of parameterized structure models. So these figures summarize their results or the results of their mean period spacing analysis. The 2 groups prefer to display the results in very different ways. So on the left, you have the mean period spacing versus effective temperature with different evolutionary tracks for different white dwarf masses passing through here. And then these 2 points indicate the locations of 2 different spectroscopic temperature constraints and our measured mean period spacing. And you see that between these 2 points, we sort of determine a white dwarf mass in the range of sort of 0.6 to 0.7 solar masses or so. And on the right, you see similar results from the Texas group, where the color contours show the quality of the fit to the measured mean period spacing through model mass and effective temperature space. Here again, we see that the best fits that agree with now the spectroscopic constraints are here. This sort of agrees in, again, the range 0.6 to 0.7 solar masses. The jaggedness in both of these figures just comes from the way that the models are interpolated for display. So both groups also performed period by period asteroseismic fits. And while we didn't identify an individual best fit model that really stood out from all the others, the best solutions from both sets of models were very similar. Some of these are marked in the plot from the Texas group by these white and black points. And we conclude from this level of agreement between the 2 analyses that the choice of which models to use doesn't introduce some dominant systematic error to the results of white dwarf seismology. So it's a bit of a validation of the method. But after we published this demonstration, really showing the current state of the art for DBV seismology as a TESS consortium, I began to think about how we might improve things. And so I'm going to share with you now for the first time some preliminary work I've been doing with Agnes Bischoff-Kim to do just that, starting with improving the statistical analysis of mean period spacings which I asked Agnes to calculate for me for a large grid of asteroseismic models with different interior structures. And here is, so at least in my opinion, this is a bit of a cleaner way to represent what the mean period spacing looks like as a function of mass and effective temperature. These solid lines show the average, show what the average mean period spacing is through this mass and effective temperature space. And the color in the background shows the corresponding standard deviation of period spacing. The little blue points show the sampling of the grid in mass and effective temperature. So in this format, we can readily obtain a statistical distribution of likelihoods through this space for a given mean period spacing measurement and uncertainty, just through some likelihood estimation. So here's the first application of this. For the 38.1 plus or minus 1 second mean period spacing that we measured just previously for the TESS DBV that we've been looking at. So you see that the measured mean period spacing is consistent with more massive stars at lower temperatures, less massive stars at higher temperatures, but there's this monotonic variation there. And we could acquire an asteroseismic mass immediately if we had some independent temperature constraint, such as from the spectroscopic method. But I prefer not to depend on the spectroscopic temperatures for this, because I'm wary of systematics that may be present in those results, as I mentioned earlier. So instead, I've decided to turn to the astrometric data that have recently become available from Gaia. Gaia provides a parallax measurement that can be turned into a distance constraint, which then allows us to convert an observed apparent magnitude into an absolute magnitude. And I'm showing here two stars, a little cartoonish. These both have the same parallax and absolute magnitude. One is hotter and smaller, and one is larger and cooler. They could be at the same distance and appear the same brightness in some photometric band. It's got me thinking, isn't this exactly the opposite trend that we saw in the mean period spacing? Because larger white dwarfs are less massive ones. I thought that this could complement those asteroseismic measures very nicely. And so here, again, is the set of structural models that are consistent with a measured mean period spacing in mass and effective temperature space. And here are the models that are consistent with an absolute magnitude constraint. And these intersect each other at a unique location. And if we bring those together under a single probabilistic analysis, we are able to see what the constraints on the global white dwarf parameters of mass and effective temperature are. And here it is. This is emphatically a preliminary result of this new approach. There's a unique solution here, and we can marginalize over each dimension to get these distributions, probability distributions of effective temperature and mass. Effective temperature is constrained to about 500 Kelvin uncertainty. The mass is constrained to around 1/100th of a solar mass, which is quite good. So this importantly did not rely at all on the spectroscopic method, which is people have concerns about the presence of systematics, either from the models or from the fitting. And so my hope is that this spectroscopic method, which is applicable to a handful of stars that have a really rich pulsation spectra, can be used to calibrate the spectroscopic method, as I do not think that this approach suffers the same systematics. The method handles uncertainty in stellar structure and photometric extinction well by just marginalizing over their distributions. Every point in mass and effective temperature here corresponds to thousands of structural models. And yeah, so this is some work I've been wrapping up with my colleague Anya's, and I look forward to a paper describing this soon, and applications to additional stars after that. And so finally, in my last couple of minutes, I just want to tease another project that I've begun more recently at UW with post-bachelor student Tom Hemphill to similarly characterize using combined TESS and Gaia data, short period white dwarf binaries. And in particular, I want to understand better these extremely low mass white dwarfs that are formed when most of their mass is stripped off by their orbital companion to have masses of less than like 0.3 solar masses. So I don't have time to get much into the details, but many of these binaries show a photometric signal at half of their orbital period because of tidal deformation of the primary star by their close companion. You see here a figure of the folded brightness variations of the brightness variations of a white dwarf binary folded on the orbital period measured from radial velocity. And there's two local maxima of brightness that correspond to these moments in this cartoon where this tidally distorted primary star in a teardrop shape has a larger projected size on the sky because of the angle we're viewing it at. And this level of distortion allows us to characterize the radius of the primary star and also other binary system parameters, especially the inclination. So here I show a little interactive plot that I set up to kind of teach some of my students about ellipsoidal variations. One of the most important of these parameters for deciding how large of a signal we expect to see from ellipsoidal variations is the orbital inclination, right? If we're looking at a binary face on, we're not going to see any variation in the projected size of a distorted star. And so observing ellipsoidal variations gives us a way to constrain the inclination of a binary, which is otherwise very difficult to determine. And this can remove the Sinai ambiguity that is present on the secondary mass, the actual speed of the orbit, which goes into the separation between the two stars. And so what I'm doing with this student, Tom, is beginning a Markov chain Monte Carlo approach to connecting all the way through from stellar evolutionary models of low mass white dwarfs to synthetic photometry to this photometric binary model shown here, all of which will be compared simultaneously to TESS photometry, Gaia astrometry, and ground-based radial velocity and survey photometry measurements. And together, we're going to refine the constraints on a number of known extremely low mass white dwarf binaries. And these constraints will be really helpful for especially understanding the properties of the typically unseen population of secondary stars in these binaries, which is important for understanding their prior and future evolution, both of which are of interest to me because these extremely low mass white dwarfs were formed by having mass stripped off by their companions, but they also will likely merge within a Hubble time. So it's another project and another student to keep an eye out for in the literature. And so those are just a few ways that I've been thinking lately to bring together the modern survey data from TESS and Gaia to really improve our measurements and our parameters for pulsating white dwarf stars and for white dwarf binaries. So I hope that something in there caught your interest or might even be relevant to your own work. And I really thank you for your attention.
Thank you so much, Keaton. For the people that is following the talk on YouTube, thank you very much for joining us. If you have any questions, please post them in the YouTube channel and our speaker will answer them later. So thank you very much.